Yeah, that's what I'm talking
Otis
about.
is just a little bit shorter than that though.
I don't know, I saw one. One that has dark hair. Otis must look like you. That's the one that has the curlier hair, right?
All right, as for today, gonna finish up chapter 4, graphing.
Yeah, Otis looks like me.
This is the last bit of graphing, and then we're transitioning to polynomial algebra, and that's basically the rest of the semester.
Polynomial?
Polynomial.
I don't like the way that sounds. Can we skip it?
Yeah, I was gonna say, stop making up words, dude.
So we looked at graphing inequalities in one dimension, right? Now we're going to graph inequalities in 2 dimensions.
Cool.
Everything starts the same, but the big part is how we react to the line. Also as a note, so we have just a note on the calculator commands, all right? The y equal, and then you change the equal piece, all right? And you can adjust this in your calculator. Happy to show you guys how to do that if you want some assistance there. So let's start with graphing our standard y equals 2x minus 3. We should be getting pretty good at graphing now, right? Y equals 2x minus 3. What do I graph first?
The -3. The y-intercept is -3.
The y-intercept is almost -3.
0,
0, -3. We plot that 1 point, then what's the slope here?
2/1.
2/1. So I just start counting that away. And that's basically what we've been doing for 3 weeks now, right? Is graphing simple, all right, linear equations, a line, all right? By far, one of the biggest concepts, all right, in all of algebra is graphing a standard line. What we are gonna do now is take that up a notch. So we still have almost the same equation. Notice the difference between these two. Y equals 2x minus 3, y greater than 2x minus 3. This is now an inequality equation. The basics still start the same, right? We have our y-intercept at 0, -3, and our slope is 2/1. We're gonna have a slight adjustment here. So I'm gonna still plot, count the rise over the run, all right, plot the points. But, all right, we wanna think back to what we did in one dimension, right? So when it was x greater than 1, how did we draw this in our 1D graph?
It was an open circle in that way.
Open circle, all right, and which way?
Right.
To the right. It's like, yeah, it was like, you are pointing correctly. So, All right, when we move this to 2 dimensions, that means we need the equivalent of an open circle. All right, for a line, an open circle is basically a dashed line or dotted line, however you want to identify that. This is what represents an open circle in 2 dimensions.
I don't like that.
Okay.
All right. Because the line, just like here, x is greater than 1, not including. This is saying the line y is greater than the line, but not including. Then we need the other part. Now, there's 2 ways to do this. Essentially, we need to identify a true value. So basically, let's pick the point 0, 0, because that one's an easy one. 0 for x and 0 for y. And I'm gonna plug those in. So on the left side, I end up with 0. 2 times 0 is 0, minus 3 is -3. Is 0 greater than -3? Is that a true statement?
Yeah, yes.
Yes, that essentially means I would shade the point 0, 0. And I can test it for a lot of points, but essentially there's only 2 options. To the left up of the line and right below the line. That means everything to the left of this line is true. The other way to really identify this, right, is when you read this out, y is greater than the line. And so I kind of like to be like, oh, that means I just shade above, right? Everything above is colored in. This arrow means that all those values are included. That means the solution is everything above the line. Now, you can always test a point, but when we start doing more and more lines together, it's usually just better to read it out as shade above the line, shade below the line. There's only going to be 2 options. And now all that shaded region is actually the solution, excluding the line because it is a quote open circle dashed line. Let's do that again, but now notice the inequality is changing. We still have the same line again. All right, but now notice y is less than or equal to 2x minus 3. So remember when we had that? So if I had x less than or equal to 1, how did we represent that in 1 dimension?
It was a full, like a filled in circle.
A filled in circle and then going left.
Oh, going left, yes.
So this, all right, the equivalent of a filled in circle is a completed line. So we are including the line. And then we need to identify the shading because the shading represents the rest of that region. And again, as long as you always write it in y equals mx plus b form, then it reads out shade below the line, right? So that means I shade over here. And I can do the same thing when I pick the point. Because when I pick the point 0, 0, is 0 less than or equal to -3?
Yes.
No.
No,
No.
that's a false statement, which basically that says don't shade 0, 0. So I would shade the other side.
Okay.
And so that's how that pick the point part works, all right? When you have a true statement, you shade that point and everything around it. When you have a false statement, you don't shade that point or anything around it. So it's just one additional test, all right, as we solve the equation. What is way more fun is when we have multiple lines. All right, so when we have not just one, but several lines, all right, we need to find their intersections, all right, and then identify what we call the true region, the solution region. Because you don't just shade all above this line, all above this line, right? Because when you start having 3, 4, 5 lines, your whole graph ends up shaded. We only shade the complete solution region with all the lines included. This is how the arrow thing really helps, and you're gonna see, all right? When we start graphing this, we identify one and another, and then you can pick a point if you want. Couple other things we want to identify. So almost always we need to find the corner points, right, of the solution region. That's just the intersection. That's what we were doing last time, all right, as well as back in chapter 3. And then we identify if a region is bounded or unbounded, all right? It's exactly like it sounds. Bounded means enclosed. What is the minimum number of lines you need to make a shape?
3.
3. What shape is that? A triangle. All right. So, and then of course, as long as you have more than that, then you can make additional shapes. But you identify what is the solution region, and if it goes forever, all right, then it's unbounded. If it is enclosed, then it is bounded. All right. So let's look at an example here. So I have 2 equations. And the idea with these 2 equations, as always, solve them y equals mx plus b. All right, so for my red line here, I bring the negative 2x over, right? And then what important thing must we do?
Divide by -1.
Divide by -1. Does that have any implications?
Flips the inequality.
That flips the inequality. That becomes y less than 2x. All right, dividing or multiplying by a negative flips the direction of the inequality. Notice that I can add and subtract negatives all day long. That doesn't change the inequality's direction. Okay, but when you divide or multiply by a negative value, that changes the direction of the inequality. All right, so let's start with our blue line. Where do we what is the y-intercept?
0, 6.
Oh, we're gonna get it. And then what is our slope?
Is
-1/1. All right, it's always a tricky one, right? Because it's just -x. Don't forget, there's a hidden -1/1 there. And I have plenty of people that just write it out. I was like, if you want it super specific, right? That is the same thing, all right? Just to emphasize for myself, that is the slope. All right, so -1/1. Is this line dashed or solid?
Solid.
Solid, because we have the greater than or equal to. Then, are we shading above or below this line?
greater than.
Above.
Above. And if, as long as you always write it in y equals mx plus b, and you basically just say it out, shade blank the line. Whichever way it's facing, all right? If it's facing towards the y, that's above. If it's facing towards, away from the y, that's below. All right, so we're gonna shade above, but we're not gonna shade this yet because we have so this, I'm just telling myself later, I need to shade above. Because I'm trying to find the complete solution region with both of these lines together. All right, the other one. so y less than 2x. So what is the y-intercept on this one?
0, 0.
0, 0, well done. Then what is the slope?
2.
2/1.
2/1. Be aware, technically 2 is correct, right? We just like to say it as 2/1. Then is this line solid or dashed?
Dash.
Dashed. Okay, and then am I shading above or below this line?
Below.
Below, right? Shade below the line.
So it's just gonna be that little area between the two of them?
Right, so that is the question. So where these two come together? Is it over here?
No.
Is it down here? Is it over here?
Yes.
Where both of them, right? I'm shading above this one and below this one, right? So it's only this region right here is the solution. And be aware, I want to make emphasis that this does shade below. I see a lot of people, they shade to here and stop. The axis is just there as a helper for us graphing, right? It doesn't actually have anything to do with the solution region in this case. All right, so we have a couple questions to answer. Is this bounded or unbounded?
Unbounded.
Unbounded, right? By definition, we only have two lines. That means this goes on forever. The other thing we want to identify are the corner points. Now, this happens to be a nice one. What is the intersection point of these two lines?
2, 4.
2, 4. All right, if you didn't draw a good enough graph, what could you do?
Solve it with algebra.
Solve it algebraically. Okay, never hurts to do that, but I was like, we have a pretty nice graph. All right, and I can clearly see that is the intersection point 2, 4. The corner, all right, are there any other corners? No. I was like, two lines, they intersected a single point, all right? That is the only corner point and it is unbounded, it goes forever. Those are basically always the directions, okay? Identify the solutions, bounded or unbounded, and the corner points. One other note. Technically, this right here, since this is a dashed line, does it actually touch the point 2, 4? No, okay? We write it as the corner because it gets so infinitesimally close, right? That essentially it's the 0.24, but just so you know, it actually never touches the 0.24.
Is that?
All right. Now we're getting more and more lines. So, all right, I see three kind of normal lines. Then x greater than or equal to 0, y greater than or equal to 0. X greater than or equal to 0. What kind of line is that? That is a vertical line, okay? That's a vertical line at what point?
0.
0, okay? We also refer to x equals 0 as what? What is that on the graph?
No.
X equals. No, not a corner.
Oh, damn it.
This is x equals 0.
Oh, it's the y-axis.
It's the y-axis. Y equals 0.
It's the x-axis.
It's the x-axis, okay? If x is greater than 0 and y is greater than 0, what quadrant are we in?
None.
1.
1, because I'm above this line and I'm above this line. That means this whole graph takes place in the first quadrant.
Is that right? This one doesn't have any-
That's why this one doesn't have any lines, because if you're only in the first quadrant, should you draw the normal axes? Oh,
I would like to though. Please.
your graph is gonna end up this small. So it's important to understand, all right, what we're looking at, and this is the whole concept of context.
I know, I just don't
We talked about it. In the real world, are most numbers positive?
Yes.
Yes, actually. I was like, time, distance, I was like, we had some examples, profit is negative. But most things, actually, when we start doing contextual graphing, we're in the first quadrant. So we graphed both of those. All right, let's see our other graphs.
We just pulled the pieces out of it.
Go ahead. I'm just solving them y equals mx plus b.
My brain was catching up, yep.
Now, one of the other things, since we are all in the first quadrant and actually all of these lines have a negative slope. So actually, all these lines are basically, looks like they're gonna cross through both x and y. What might be helpful is to identify the x and y intercepts and use that as graphing, all right? Instead of doing our standard do the slope. So remember the cover-up method, the y-intercept, 0.22. What is the x-intercept here?
-2/1.
No, not the slope, the x-intercept.
That X is greater than or equal to 11.
Just 11, yeah. We're just looking for the intercept, nothing to do, has nothing to do with the inequality at this point, right? So just doing the cover-up method, 2x, right? So 11, 0, right? What's the y-intercept here?
Greater, wait.
0.13.
0.13.
What's the x-intercept?
0 or 13, 0.
Yeah. What's the y-intercept?
0.10.
What's the x-intercept?
25, 0.
Yeah. Does everyone see the math we're doing really fast?
Yeah.
Right? 2x equals 50, divide by 2. All right? 5y equals 50, divide by 5. I was like, you can, right, the cover-up method, you can find the intercepts, right, which was also on the quiz. You can find the intercepts super fast. I'm doing this because what this identifies is actually these numbers are not beautiful like we have been looking at. Also, when I see a value of 25, does my graph go that big?
I don't know, I haven't counted.
It's definitely not 25 squares, right? It's 10 by 10, it's about 20. 10 and 10 when we do normal axes. So the idea here is that also sometimes you might need to adjust your scale. So let's go by 2s.
250 divided by 2. And it's 2x equals 50. Divided by 2.
Still doesn't get us.
Alright, so each box now represents a 2, but I scaled it by 4s just because I didn't have enough space to write 2, 4, 6, 8.
Oh, that's what I did wrong.
Now we can actually graph intercept to intercept. So for the black line, that's 11, 0, which is right here. No, 0.22 is right there. 0.22, which is right there, and then 11.0, which is right here. Zero 13 and 13.0. Zero 10, 25.0. So just graphing with the intercepts. This is a very common approach, right? When you're completely contained in the first quadrant.
And they're all gonna be solid lines, right?
They're all solid lines. Excellent. How did you know that, Anna?
The greater than one.
Yeah. The equality, all right, is included on all of these. All right, none of these are a strict inequality. They're all less than or equal to's. Along those lines, where am I shading above or below all the lines? Because they're all less than or equal to. Below, shade below the black line, shade below the blue line, shade below the red line.
So it's gonna be this.
Right, so below means that the shaded region is this guy. Now, the good news, here's the other thing. We've already found some of the corner points. Okay, let's start with these things. Is this bounded or unbounded?
Unbounded.
Bounded. Does it go forever?
Oh, I forgot about those ones, yeah. Okay.
No.
No, just closed in.
It is closed in, right? It is a five-sided figure.
These were actually.
It's gonna be hard because they're in the middle.
Some are gonna be hard, some are gonna be easy. Let's start with the easy ones. What's the easiest one by far? Quarter points.
It's the 0, 0.
0, 0, it's right here, boom, got that one. All right. There's two more easy ones.
Is it the
11.
the 0,
11.0, right here. There's one more easy one.
0,
0, 10.
22?
All right, so we got, and that was also one of the things by identifying the intercepts initially as well. Oh, look, that helped us with some of our corners. Now we have slightly more complicated ones. So yes, it might be that, but notice that kind of like, yeah, I mean, 9.4 maybe? I'm not sure, which means what do we need to do?
Plug it in.
Algebra. Specifically, okay, so let's start, all right, let's start with the cross of the red line and the blue line. It's also why the colors are helpful here. All right, so the blue line. So I'm gonna set y equal to y, red equal to blue. So what was it, negative x plus 13?
So we're just using an equal sign instead of an inequality now?
Yes, because we're actually finding where they cross, right? So finding intersection points is always the same. It's still equalities. There's no inequality needed. The inequality only indicates shading. Otherwise, everything we do you can still just do equalities. Technically, you could still write the lines as equalities and just be like shade below y equals negative 2x plus 22. I was like, that's all the inequality is representing. Where to shade on the graph. All right, so some fun algebra. Well, how do we solve it?
Well, then you would minus, or you would plus X on both sides and minus 10 for both sides. Leaves you with 3, 1 and 2/5 X.
I would get rid of that fraction.
Well, I mean, we should be able to do this. X minus 2/5 X, 3/5 X, right? Right? 1 minus,
Plus X.
you guys with me?
But it's plus an
Oh,
X,
so then.
not minus. Oh, it's negative up top.
It's negative up top. So it's really 1 minus 2/5, just 3/5, right? I was like, that's one that ideally we could do in our head.
You're right, I just got confused.
All right, then multiply by 5/3. And now look, x equals 5. Oh, it did come out to a number, that's excellent. Y equals then negative x plus 13. So negative 5, plug that in, plus 13. Gives me y equals 8, and I could plug it into the other one too, but let's just leave it there. So the intersection of that one is
5, 8.
5,8. All right, so there's one corner down. 5,8, did that look like 5,8? Pretty close, but I was like, did it look perfect? Could I identify that from the graph? No, right? What if it was a decimal? I was like, definitely want to make sure you keep solving it. All right, then we need the intersection of the blue line and the black line. Negative. And this one's even easier, actually. So plus 2x. It's 13. Oh, look at that, x equals 9.
Oh, that's negative, okay. Got it.
Yeah, the biggest thing is just keep track of your signs, right? Without a doubt. Right, Brian? Signs are the thing that you drop super easy. So everyone just, I was like, where you have a negative, where you have a positive. I was like, stuff cancels, stuff stays. And then we get to plug that in. So the 0.9 comma 4. This is where the colors are super helpful because it's like this line to this line. So if you're doing it all in one color, sometimes I see people identify what might be helpful is this one was Y1, this one was Y2, this one was Y3. So that way, even when you draw them, oh, I need to set Y1 equal to Y2, and then I need to, because otherwise you'll like get an intersection and maybe if you accidentally solved the wrong two lines, you found this intersection, right? So make sure you're trying to find the corners that you actually desire. And then, so that lastly, that was 9 comma 4. Does that look like 9 comma? Actually, I think we said 9 comma 4 is like the reasonable guess, right? But it's not perfect, all right? When you start messing with your scale and things like that, all right, we can draw the best line we can. Always use the algebra to confirm where they actually cross. So 5 corners, all right, it is bounded and we have the region shaded. Beautiful, huh? Yes, Brett.
How would you find the point of letting line?
Oh, excellent. That is a wonderful point. Because that's not included in the region. I could find that just for kicks, right? But we're only looking for the corners of the solution region of the shaded area. Notice that I have that one, this guy. I have lots of points that aren't included in the shaded region. We don't care about those because they're not part of the solution. All right.
It's part of the problem.
Good answer.
I was like, for practice, we can always find more.
No, it's not.
All right, and then as always, the best part. Word problems. A company uses sedans and minivans to produce custom vehicles for transporting hotel guests to and from airports. Plant A can produce 10 sedans per week. Plant B can produce 8 sedans per week. How many weeks should each plant be operated to produce at least 400 sedans? Express your answer with a linear inequality with appropriate non-negative restrictions. So I added that, but initially you should always be able to do this on your own. Non-negative restrictions. All right, so we're talking about sedans and weeks. Okay, so with sedans and weeks, can either of those be negative?
No.
No. So by definition, I know, all right, that I'm in the first quadrant. So I can draw that on my graph without even having to read anything else.
Is there a reason you always go to the second one?
Because I draw big. All right, in the wording here, what indicates that this is an inequality versus just equality? Just, you know, y equals 5x plus 7.
At least 400.
At least, okay, right? This is what I was emphasizing on the quiz. At least, at most, all right? Make sure that you're paying attention to that wording, okay? That's what indicates this is an inequality. Okay. All right, so let's see, how do we want to do this?
400 We don't.
Okay, so if we have sedans, right, so let's see it. Is X equal number of weeks?
Yeah.
Okay, actually, let's do it like this. Plant A, right, produces 10 sedans per week. Plant B produces 8 sedans per week. All right, we wanna, this is actually a minimum, all right, of 400 sedans. And then, so I guess we'll do X and Y. X equals number of weeks at plant A. Y equals number of weeks plant B. So as a note, all right, if we're identifying the number of weeks at plant A and the number of weeks at plant B, I would just create that. That means 10, okay, X plus 8, Y, 10 sedans per week times the number of weeks plus 8 sedans per week times the number of weeks. And then I have the 400. Which way does the inequality face?
At least.
At least, yes.
So greater than.
So the alligator mouth, is it this way or is it this way?
Facing.
Facing the equation. All right, and important note, at least means including the 400, so that is a greater than or equal to, right? For it to be strictly greater than 400, what would it have to say? It wouldn't say at least 400 sedans, it would say.
400.
It would just say to produce 400, right?
Well, that was if equality. What if I wanted to say greater than 400? What would the wording be?
More than.
More than 400, right? Okay, less than 400, at most 400. So again, those differences, all right, change the direction the inequality faces and whether it has an equality with it or not. All right, so this is another one where the cover-up method, since we're in one dimension, actually is pretty helpful. Okay, so our y-intercept. All right, what is it?
I don't know. Oh, 40.
40.
Oh, Y, not X.
Y-intercept. 400 divided by 8. Yeah, 50.
I was covering up the wrong one.
For the x-intercept, now it's 40. Right? Does everyone see what we're doing with the cover-up method? It is literally, I cover this one up and I have 8y equals 400 and I solve that. So 400 divided by 8, I was like, I get 50. And then 10x equals 400, divide that by 10, 40. I was like, you can graph these super, super fast. All right, and 40 is there. Actually, it doesn't matter. 50 is there. Because the best part about this is I only have one line and it crosses at those points. So I really just need to identify, am I shading above or below this line? Now, technically, we didn't solve it y equals, but it's not actually going to change anything.
It's below.
Okay, should we solve it y equals?
At least greater than.
Oh, it's above.
So 400 or more. That's so unbound.
All right, so do we shade? All right, now I have this y equals mx plus b. Do I shade above or below this line? Shade above the line. Which means,
You're shading a lot of this.
and yes, this is another one. So what are my corner points?
0. No, I mean, whoa, sorry.
Yeah, 0, 50, 0, 40. We actually already found them. Is this bounded or unbounded?
It's unbounded.
Unbounded.
And
And what?
so.
The nice thing about this, we only had one equation, all right? As long as technically there were 3 lines there, because don't forget, we actually had x greater than or equal to 0, y greater than or equal to 0, all right? Number of weeks at plant A, number of weeks at plant B, all right? But it didn't even matter. Just recognizing the context, knowing this is sedans and weeks, I know I'm in the first quadrant. And that is a super, super common restriction on contextual problems. Once you're there, we almost always use this approach. Identify the intercepts, graph the lines, and then just shade above, below, wherever, whatever it is, all right? This is very, very common, all right? And that's what we graph most of the time in statistics. It's almost always in the first quadrant because that's where real data exists.
So is that the X and Y intercepts are just the number of weeks?
The number of weeks that would be spent to reach that goal, right? If I spent 0 weeks, right? So contextually, if I spent 0 weeks, or was this plant A or B? Anything? 0 weeks at plant B and 40 weeks at plant A. How many sedans do I make?
At least 400.
Oh, at this point, exactly 400, right? That is the minimum, but that is the at least, right? If I spent 0 weeks at plant A and 50 weeks at plant B, I make exactly 400 sedans. Then everything out here is more than that, right? I'm making more than 400 sedans. So that's all these situations. Now, this is not like our other word problems where you can't really, I mean, I could say those examples, but there's literally an infinite number of solutions, right? 100 weeks at plant A and 100 weeks at plant B will produce some number that's more than 400 sedans, right? So the solution to this, all right, actually is the graph, All right, and I'm glad you brought that up because, yeah, we don't have to put a sentence on this and there is no more context, but you need to see how the graph relates, all right, to the context of the problem. All right. So much good stuff. Cool. All right, another wonderful activity for you guys to take a look at.